Okay, so great. We're actually going to get our hands on some data and run some statistical tests today. Uh, uh, but where we're going to start is just with some high-level ideas. What we've seen so far is this idea of making inferences about a population mean when we don't actually all we have are the draws from the random variable. So we don't know what the random variable is. We don't know what the population mean is, and we don't know what the population standard deviation is. All we have are the samples. And what you've shown on the mini exam just now is that you can differentiate between the sample, the sampling distribution, and the population. And then be able to use those ideas, the separation between these ideas, to make probabilistic claims about population parameters, like the population mean. But what we're doing today, I'm going to show you how all of these ideas are simplifications, or they're a simple version of a much more general model, which is what we're about to do. Everything we do from here on out relies on your understanding of the difference between the sampling distribution and the population distribution. What happens when we take a sample? How does that sample parameter, whatever the parameter is, how is that related probabilistically to the population? Okay, so this is what we just did. We developed our first general linear model. I'm going to show you how we actually run these things in practice. How many of you have actually run a t-test? Like on a computer, run a t-test on some data? Hands high, proudly. You've done good work. Okay, so nice. So I'm going to show you the way that we actually run these things. We generally don't run t-tests, at least in economics, using like the t-test function. We do it in a different way. And I'm going to show you how and why. And it turns out this is good news. This is not, I'm actually making your life simpler by making this connection. This is how I think about these things, and I'm hoping you'll leave with these skills. So the first question I want to present to you is, what's a GLM, the general linear model? Essentially, a general linear model is just, we take data. We spent like the first, third to half of the semester just talking about how to visualize data. All we're going to do with a general linear model is take that data that we've visualized and draw a line through it. It's really not that much more complicated than this claim. General linear model, we're just going to draw a line through data. It is a little more complicated. Generally, when we work with a general linear model, we have lines. You all remember your high school algebra class. So we have lines, and all we're doing is drawing lines on the data. We have an equation for a line, which is something like this. So this is 2 dimensions. We have an x and a y, which you can remember back to Seaborn. Seaborn actually asks you for x and y, right? These are the same x's and y's. And then we have mx plus b, just our standard equation for a line. Some terminology here, our y is our outcome variable. So in part 3, all we've dealt with is a y variable. For statistical reasons that slightly baffle me, we usually use, we use x bar to denote the sample mean. I think of x bar on the mini exam as a y bar. It's actually the outcome variable, and we typically represent this on the vertical axis. So we're gonna switch things around a little bit today, just x and y, for that reason. But our y variable is what we call the outcome variable, and we typically use this on we represent this on the vertical axis. In this class, we're only going to use numerical variables as our y variables. Y variables in this class will always be numerical. there's a sort of technical reason why we only focus on numerical outcome variables. You can it becomes much more complicated to deal with categorical data as an outcome variable. So all semester we're going to do numerical variables as the outcome variable, but our x variable, what we call the predictor variable, we can have either categorical or numerical variables. So we're going to talk about how we deal with numerical predictors. So what happens when x is numerical and what happens when x is categorical. And we're going to be able to deal with all of these things with the general linear model. Some equation that looks like this. We can have more complicated versions of lines. So we're about to start talking about bivariate data, which looks like this. But we can have multivariate general linear models. So could look like this. So we can have multiple x's that are predicting y. And we're going to talk about this. How many of you have run a regression before? Hands high, proudly. Nice. Okay, so we're going to talk about multivariate regression and then, or sorry, bivariate regression and then multivariate, which is what we'll do in part 5. Okay, so nice. And if you want to be fancy, you put these little subscripts at the bottom. Each one of these i's is just telling us which individual data point. And then we have this little epsilon at the end, which is what we call the error term, which we'll talk about more in a second. So if you've run regressions, some of this will be a review. If you haven't run regression, this may be new information. If this is review for you, what I'm hoping to convey to you is some of the deeper intuition for what's actually going on with choosing the parameters. So how do we actually fit the line? Which is a big part of what we do. In understanding what the regression is telling us depends on understanding how it was constructed. So part 5 will be very difficult if the intuition doesn't happen for you in part 4. Okay, so how do we choose this line? Like, this is the big question, right? It's like, how do we have a line, we run the line through data, but we could run the line through data in any given way we wish, like vertical, horizontal, or anywhere in between. So how do we pick it? We try to minimize how wrong our model is. That's the core idea. We want to draw a line so that the wrongness of the model is minimized. And the way we measure wrongness is with this thing, what we call the mean squared error. How many of you have seen MSE before? Okay, nice. This is our measure of wrongness, which I'm going to show you a picture of what this represents. But this error term is essentially just how far away our data point is, any given data point, is from the model itself. This is a very similar idea to the variance. But I'm going to show you a picture of how to understand this intuitively. It looks terrible. Essentially, this is just the average distance squared between our data point and the line. So we're drawing a line, we're drawing a distance between the line and the data point. We're taking that distance and we're squaring it, and then we're taking the average of those things. So very similar to a variance. Squared, average squares is how we measure variance too. Okay. So with the picture I'm about to show you, we're going to set up the very simplest general linear model. So we're actually not going to work with x. We're going to say there is no x variable. All we're going to do is have an intercept term. And then we're going to try to choose where the intercept term lies. So our data, xi, so each individual observation, xi, is in blue. So this is just the raw data. We have our model, which I'm telling you is just an intercept term. So we're drawing a line, there's no slope to it, it's just horizontal. I have a student in the class that comes after you who really dislikes when it's sort of a running joke, when I don't include the axis labels. Like on a histogram, I usually just take off the count on the vertical axis and don't actually report anything. So it's a running joke that like I don't like them and the student loves them. Here, I'm taking out the horizontal axis because the index doesn't matter. So all we're trying to do is think about the vertical axis, and all I'm doing on the horizontal axis is just indexing them. So I have a bunch of data, and the running example for today is just the difference between wait times. So I had, I think that this was 50 people go to a restaurant, order in the morning, and then order in the afternoon. And then I just took the difference in their wait times in the morning and afternoon. So this is just wait time differences. And so we have a bunch of wait time. So positive values just means the person waited longer in the afternoon than in the morning. Okay, so if we choose a b that's large, so b is equal to 2.5, so this is just the intercept is running through 2.5. What I've done here is plot out the error terms in green. So the model is in red, and then the error terms are in green. So the difference between the model and the data point is just the vertical distance between those two, between the data and the model. And then to calculate the mean squared error, all we do is we go through and we take the average square of these things. So we take the value, we square it, and then we take the average of those squares. If we choose a large value, we get the error terms for the data below the average, below the model, come out to be much larger. So as we lift this up, we're increasing the error of the smaller values, and we're shrinking the error, my goodness, of the larger values. And then if we choose a small value, we're increasing the error of the large values and then decreasing the error of the small values. Right, so depending where we move this, the error gets larger or smaller. Anyone know how our goal is to try to minimize the average squared error. Anyone know what value we would pick if we're trying to minimize the mean squared error? How do we be as the least wrong as possible? Sabi?
I'm not sure if this is right, but maybe choose a model that's closer to the majority amount of data points.
Yeah, so intuitively we want this line to be somewhere that's close to most things. Yeah. There's an actual like mathematical concept that we that minimizes the mean squared error. Anyone know what that is? Savi is like generally right here. So unfortunately no lecture points. I will claim without proof, there's proof in any good textbook that we would pick B at the mean. So we're going to pick B at the mean Y value, which captures some of Sabi's idea here of picking a model that's close to the middle point of the data. And this is just a picture that shows what happens to the mean squared error as we move away from the mean. So here I have the wait time differences. I've plotted a line through the middle of the data at the mean. I've plotted out all of the error terms. And then I have this nice little figure over here. And you can see as soon as we move away from the mean, which I've plotted at this red point, on the vertical axis, we get a larger mean squared error. So if we move in either direction, we either increase above the mean or we decrease below the mean. Our mean squared error goes up. How many of you know convex optimization? Like optimizing a function, like from Calc 1. All we're doing here, we can define all these things mathematically, take a first derivative of this, and find the minimum of the mean squared error. So if you're interested how we arrive at the mean, it literally just comes from a first derivative of the mean squared error. So if you're interested in that stuff, that's how we prove it, actually. That's part of why we use the square and not the absolute value. It's because the absolute value does not have a derivative. But here, all we want to find is the lowest point, and that happens exactly at the mean. Okay, we're not doing any of that optimization in this class. All we're talking about are the ideas. Any questions here? Savi?
I have a technical question. So when you mentioned that we find the first derivative of the MSE,
Yeah.
so it's basically like finding the differentiation when the rate of change is kind of like 0, so that we're not changing the error too much. Is it like that?
Yes, similar. So we would take a derivative of the MSE with respect to B.
Okay.
Yeah, so we try to pick B so that it minimizes the function, which in this case is the mean squared error. So our x variable that we take a derivative with respect to is B on the horizontal. But we're not doing any of that. So if you don't like that stuff, you don't need to know it. Okay, any other questions here? Okay, so what have we done? We've talked about lines. We've drawn a line through data. We've found the line that minimizes the mean squared error, the wrongness of our model. And it turns out the best model is this thing, where we choose a vertical intercept exactly at y bar. Does this remind you of something we just did? If I were to run this a bunch of times, be thinking about what we just did in part 3. If I run a bunch of samples, each sample, like we've talked about in the past, has a slightly different sample mean. And then I plot that sample mean, and I fit the model, I get a different parameter. So the mean in each one of these is different, simply due to sample variation. Remember the die roll experiment we did in class. Every time we take a new sample, the sample mean is different, which means every time we run the general linear model, our vertical intercept will be different. So if I were to run 1,000 samples, run a general linear model on each one of those samples, and plot the model, RB, we could plot a histogram of the vertical intercepts. Any ideas about what that might look like? What happens? What would you expect? Actually, tell your neighbor what would you expect if I were to plot a histogram of B for each one of these samples? I run this 1,000 times and construct a histogram. What does that look like? All right, someone tell me. I'm on the next slide, if my memory serves. I have a histogram of not just these 8, but 1,000 samples, and the sample, the B, the statistical model for each one of these samples. So I fit the model and plot the B. What does that distribution look like? Yeah, Sophia. Approximately normal. So I'm going to plot this. This is the distribution of B's, the intercept parameter on our general linear model. Why is this true? Someone tell me why. why do we see such a nice distribution of intercept parameters? Isn't this cool? What does Katniss Everdeen say? Are you not amused? The reason this is approximately normal is because the intercept parameters are all the sample means. That vertical intercept is just exactly the sample mean. So when we took samples and we plotted the means, we got an approximately normal distribution. That was given to us by the central limit theorem. This is just the same idea in disguise. B is just the sample mean because we're minimizing the sum of squared errors. We're fitting the line through the data horizontally, where the x variable has no meaning. So we're just picking a vertical intercept that's equal to the sample means. We plot the distribution of that intercept parameter b, and it perfectly matches the distribution. It's centered on the truth. It has a nice bell shape from the normal distribution. I call this a t distribution, but with sample sizes this large, it doesn't matter. Any questions here? So, minimizing the sum of squared errors gives us an intercept that's exactly equal to the sample mean. That intercept term follows a t distribution, or normal distribution if our size is large enough. And it's centered on the truth. What this means is we can make statistical tests of the parameters in our models. So we're no longer just testing the means, we're testing the parameters in our model. We know the distribution of these parameters under the ideas we've developed in the class. We don't observe the truth, and we don't typically observe a bunch of 1,000 random samples like I've drawn here. Typically, all we observe is what I've highlighted, which is one sample, just this vertical bar, which is not equal to the population mean. It's just one sample. And typically what we do, I've shown you mathematically, it's identical to center the sampling distribution on the truth or on the sample mean. So typically all we see here is just the t distribution, and that's centered on our sample mean and our sample mean. So this is the same idea, right? Everything we're doing here is exactly the same, just framed slightly differently using a horizontal line as our model. And then we're testing the probability of our model. So what I'm going to do here is test a null hypothesis of 1.8 minutes. So I see this. I see one observation. I know what the t distribution is that's centered on my null on my sample mean. And I'm curious, is this consistent with a wait time difference of 1.8 minutes, morning and afternoon? Now, the way we test this is exactly the same as what we've just done, right? It's literally the same thing. All I'm going to do to find the probability of seeing our sample mean under the null hypothesis, the intercept term under our null hypothesis of 1.8 minutes, this is the figure that we look at. And if you prefer, we could flip it vertically. But all we do, just like we did with our more traditional hypothesis testing approach, is we just find the probability in the tails. This is centering the t distribution on the sample mean, but it's equivalent to centering it on the null hypothesis. And this is the way we've talked about it primarily in the class so far. So I'm going to present it this way, but you can equivalently set it up centering the t distribution on the sample mean. So I'm going to plot, our two tails. So this is, we have our sample mean, which is our red bar. We have our null hypothesis, which is the center of the t-distribution. And then all I need is something equally extreme as our sample mean, but on the other side of the null hypothesis. And remember, the horizontal axis here is not x bar. This is our model parameter, b. And what I want to convey to you is when we move from thinking of hypothesis testing in the univariate environment, we can move directly into testing parameters of our statistical models. This is the same idea that we're going to apply to much more complicated or much more apply to statistical models with slopes. So this is just the very simplest statistical model. But the core idea is we can test the probability of seeing a coefficient in the way that we do. So we're testing the coefficient, and we can get, or the parameter, and we can get p-values. So before I put this on screen, I want you to tell your neighbor what this p-value represents. So I have a nice figure. I walked through the whole construction process. Now you tell your neighbor what this p-value represents. We don't actually have numbers here, or I didn't plot them. But imagine you knew what that p-value was. What does the p-value tell us?
Say the probability of something that's extreme is %. Just a guess. I was like trying to recite a solution on that.
Maybe useful on the mini exam.
Yeah. I was like, I knew that it would be written.
Yep. I think multiple choice is useful, but can kind of
sticks out like a sore thumb as the emotion. If it's multiple choice, like
Yeah.
it's very obvious.
Okay, someone tell me, what does this p-value mean? Like, to say it in words to someone who doesn't know statistics. Do you ever try that? Like, when you're technically proficient at something, you try to explain the thing you're technically proficient at to someone who doesn't know anything about the technicalities. It's really hard, usually. What does this p-value mean to us? Should we make this really awkward until someone answers? Not really sure how to make this any more awkward. Have I asked too many questions of you already today? Like a whole mini exam's worth? Quickly, we have an exercise to get to. We're going to run some of these models. Yeah, Hannah. Nice. Sounds like a textbook definition, which is exactly right. So it's like if the null hypothesis is true, to say this in these terms, if the wait time is exactly 1.8 minutes, what's the probability we'd see something this extreme? Okay, and you can see this from the figure. We know the t-distribution from the central limit theorem, and then our adjustment for the extra variability from the sample standard deviation. And then we have our deviation. Okay, so very nice. This is the basic idea. All we do is we run a line through our data. We know the distribution of the parameters. And the reason we know that is from the central limit theorem. So then we can make statistical claims about the probability of seeing any given parameter. That's what we're doing with a general linear model. All right. So just a bit of review here. The part of the idea here is this is the simplest version of OLS, ordinary least squares, or regression. These all are generally the same name: general linear model, regression, ordinary least squares. Where we're going in this class after this exercise, we're in part 4, which will start on Thursday. We're starting to introduce the bivariate general linear model, which involves essentially the same ideas as what we've done today. Except instead of just looking at a slope parameter, we're also looking at instead of just an intercept parameter, we're also looking at a slope parameter. And I'm going to show you the same ideas apply to the slope parameter as apply to the intercept parameter. It's all the same, just with some nuances. But we'll look at numerical predictors in part 4.2 next week. We'll look at categorical predictors. So when our x variable is categorical. We'll talk about time series. Some of you may be interested in working with time series models. And after this, after 4.3, I hope to convince you to not do that, to not work with time series. I'm going to show you why it's really complicated. I include it in this class because I want to offer some caution, some reasons to not be so bold with working with time series. And then we're going to, in part 4.4, we're going to talk about causality. So what kinds of claims can we make about causality when all we see is the data? So essentially, this is all built on the core ideas we've just talked about in the univariate general linear model case. Okay, we ready to do some testing? So what you can do, as always, is refresh your page, and you'll see part 3.5 show up, which is the simplest general linear model. I forgot to update the header, the subtitle, but you can find the notebook here. So if you click on that, it'll open our nice notebook. All right. So we're going to run some statistical tests. The first, I think for today, what we'll stick with, we'll maybe finish this up next class. So I have the difference in wait times collected here. I'm going to call this Y. So this is just a pandas data frame. I have a bunch of data here, and then I'm calling it Y. So if you run this, you'll import all of the imports, and then you can look at the weights data set, which just looks like this. And we can do lots of things to this. Just like with any other data frame, we could, find the mean, the count, the standard deviation, and so on. So this is just a description of the data. Now, when we're running statistical models, to build a general linear model, we use this package. There are multiple packages, but this is the one we're going to use in this class, called statsmodels.formula.api. And that's a lot to write out every time, so the abbreviation we use is SMF. So just like my friends in college called me Tay-Tay, you can call statsmodels formula.api SMF. Okay, So what we're going to do is run an intercept-only model. And the way we're going to do this looks like this. So the intercept-only model, we just run smf.ols, which is our ordinary least squares. So all we're doing is minimizing the sum of squared errors. And then in the first entry here, we're writing out our model. So here we have y, which is the y variable, which we've called y in our data set. And then this little squiggly symbol is to denote that this is the equals sign. So remember, our statistical model is y is equal to just the intercept b. So this is the equals. So y is equals to something. And then whenever we run OLS, there's always going to be a parameter on the x variable. By denoting 1, OLS interprets this as saying there's no variability in our data. So it's going to report to us exactly the mean whenever we put in an x of 1. So this is just enforcing that the intercept term reports the mean. So that's what this 1 is for. You don't need to think too deeply about why this is 1 for this class, but when we just want an intercept, we put the 1. And then it asks for data. So the data that we're going to give it is the weights. And because we have y as one of the column names in the dataset weights, then Python knows to use that as the column. And then all we do on the end is just ask it to fit the model. So when we're fitting the model, we're just saying, let's minimize the sum of squared errors, and that's going to report the mean. If we run this model, so let's just run this model, it gives us a nice little output here. The first thing is this, I don't know, does this look scary to you? So we're going to condense this, and I'm going to tell you what to focus on. You're going to become very familiar with these kinds of reports. But the first one is that we want to look at the coefficient. So this gives us a column for the intercept term. It gives us the coefficient. It gives us the standard error. So remember, I asked you for standard errors on your mini exam. This is just computing it for us. This is the standard error of the y variable, of the intercept term. So the standard error of the b values. And then it also gives us a coefficient. This coefficient should equal the mean. So if we go back up and we just look at the mean, so I could write out mean, it should equal the mean of the y values. So here it's 2.04, and here it's 2.04. So these are exactly the same number. So the intercept term gives us the mean. This is a p-value. But the p-value doesn't exactly, right now, whenever we run a statistical, an OLS, the general linear model will default the null to test for 0. So what this is saying is we are very, very confident that the intercept term is not 0. So unfortunately, there's not a simple way of writing in the testing for a different null hypothesis for the intercept. So what I'm going to show you is how to test for a different null hypothesis. I think this is maybe enough for today. You can take a look at some of this code if you like. But this is the very basics of getting set up fitting statistical models. We're going to come back to this. You're going to be very familiar with how to interpret these tables over the next coming weeks. But this is the very basics. I'll see you all on Thursday. congrats on your mini exam. Go treat yourself like Pavlov would and give yourself a treat.